Hello everyone. I am here to give a presentation on the economic choice of conductor size by using Kelvin's law. Like a country like India is one which is underdeveloped. So the economical point of view has to be seen in each and everything that we are just designing in. So we are just going for the design of the transmission line. The economy of the conductor materials is being used is also being considered. So thus, it becomes vital to select a proper size of the conductor because the conductor size should not increase the economical point of laying a transmission line. So the most economical design of the transmission line is for which the total annual cost is minimum. The total annual cost is one which is being divided into two parts, as we have just seen that in your first unit itself. It is one which is being depending upon the annual charges, that is depending upon the capital layout. The next one is the annual running charges. Like the annual charges of capital outlay is one which is just depending upon the interest, depreciation cost, and the cost involved for like building up the system or maintenance cost, etc. The cost of the cost involved in your energy, that is running charges. Running charges are nothing but the most important cost over here is the cost of energy loss during the operation. So the two important things that has to be considered while we're just going for the design, design of the transmission line, that to the economic point of considering the conductor size while designing the transmission line is, if suppose I'm just going to increase the cross-sectional area of the conductor. So suppose if I'm just, if the cross-sectional area of the conductor is decreased, the total capital cost of the conductor is decreasing. That is the thing. But if cross-sectional area is decreasing, obviously, the cost involved for getting this lesser cross-sectional area of the conductor is also decreasing. So what will happen if, as per the equation, R is equal to rho L by A, if the cross-sectional area is increasing, the cross-sectional area is decreasing, obviously resistance gets increases. The line loss is I square R. So thereby, if resistance is increasing, obviously the losses get increases. So if the cross-sectional area is increased, previously I told that it is decreased. So if it is increasing, obviously it will just increase the capital cost of the conductor, but the line loss will be decreases. And these two are controversy cases. Hence, the involvement of the Kelvin's law for finding the economic size of the conductor is being used. Let us just consider that the cross-section area of the conductor is considered as A, and the annual capital cost, that is involving the interest and depreciation on capital cost of the conductor, is given as C1, and the annual running charges that is involved with the energy loss in the transition line is being considered as C2. Now, as per the explanation that is being given, the annual interest and depreciation cost, that is the annual capital layout cost, is one which is proportional to the area of the conductor, area of cross section of the conductor. Hence, I can just write, let C1 be the annual capital layout cost that is proportional to A, area of cross section. So in order to remove that proportionality symbol and equate it, I am just going to introduce a constant K1, and this K1 is nothing but the coefficient of the cost, this coefficient involved in area of cross section. Similarly, the annual running charges is inversely proportional to the area of the conductor. Hence, C2 is equal to K2 divided by A. So what is the total cost? Total cost is nothing but the annual capital layout cost plus the annual running cost. So I have to add C1 and C2, hence that will be C. So C is equal to C1 plus C2, that is K1A plus K2 divided by A. For C to be minimum, the differentiation of this total cost must be done and equated to 0. Hence, if I just differentiate this, I'll get K1 is equal to K2 divided by A square. Hence, I can just rearrange this A and I can write as K1A is equal to K2 by A. So thereby we can just find the condition of obtaining a minimum conductor size is when the cost where the cost involved for the capital layout, that is including the interest and depreciation, should be equal to the cost involved in the energy loss, that is C1 is equal to C2. So the Kelvin's law states that the most economical size of the conductor is that for which the annual interest and depreciation cost is equal to the annual cost of energy loss. From that, I can just go on finding what is the equation of the area of cross section that has to be selected for obtaining an economical size of the conductor to be used for designing the transmission line. So A will be equal to square root of K2 by K1. Now this is the graphical illustration of the Kelvin's law. As the annual cost of the conductor is directly proportional to the size of the conductor, it is, as it has been told earlier, it is annual cost of the conductor is proportional to the size of the conductor. That is shown as C1, that is somewhat a linear line. And you know that the annual running cost, that is the cost involved for the energy loss, is shown as C2 because it is inversely. So you will have and slopy curve. So the total annual cost is shown above. And you can just see that the lowermost point of the total annual cost is one which is going to give you the most economical size of the conductor. And that is corresponding to the intersection of the two costs C1 and C2. So now from the graphical illustration, I can get what is the area of cross section of the conductor and what will be the annual cost. Okay, so the area of cross section is given along the x-axis, that is OA. So what is OA will be just representing the economical area of cross section of the conductor. And for this economical area of cross section of the conductor, the minimum cost, annual cost obtained will be just given by the distance xy. You, though you have Kelvin's law put forward for solving this economical selection of economical size of the conductor, it even has its own drawbacks. The limitation of this law are it's quite difficult to estimate the energy loss in the line without actual load curve, which are not available at the time of estimation. And if you just go on for the annual capital layout cost, you are just only considering the interest and the depreciation. Okay. And another one thing is it cannot be determined accurately. The conductor size that is being determined by using this Kelvin's law may not be practically applicable because it may suffer some sufficient mechanical strength, which it will not have. It will be having insufficient mechanical strength. It will not be mechanically robust. This law does not take into account several factors like the current carrying capacity, corona losses, etc. Another one thing is the economical size of the conductor may cause the voltage drop beyond the acceptable level. So we are just going to make a little bit modification of this Kelvin's law, and that is called as the modified Kelvin's law. So here the modified Kelvin's law, the Kelvin's law, in the Kelvin's law, we does not have an account of the supporting structures involved in your transmission line, the erection of the transmission line, and the insulator's cost. And it only accounts for the capital cost of the conductor and corresponding interest and depreciation. And also for the transmission line when it is in an underground fashion, that is the underground cables. The cost of insulation and laying is not considered in the actual Kelvin's law which was used previously. So in order to account for the above said cost and to get a practical fair result, the initial investment needs to be divided into two. That is, one part of the cost which is dependent on the conductor size and another part which is directly proportional to the conductor size. One part which is independent of the conductor size, another one is directly proportional to the conductor size as we have just taken in the previous one. But we have to include all other costs which is being told, which is not actually included in your Kelvin's law. So for an overhead transmission line, Insulator cost, apart from the supporting structure erection cost, insulation cost is one which is having a major thing. And when you just go on for a particular voltage, the insulation cost will be almost constant. And the cost of supporting structure and the erection is partly constant and partly proportional to the conductor size. So taking this as a point, the modified Kelvin's law can be given with two total charges. So with the two charges, one with the annual charge on the capital layout, which is being given as C1 is equal to K1 into A, which was already determined, plus K naught, which is involving the insulator cost, which is insulator cost, which is a constant, as well as the supporting structure and the erection, which is a partly constant. That one. Also, it is proportional to the conductor size, so it is taken as K1A. So K0 is representing the insulator cost and the supporting structure cost, which are partly constants. Hence, it is not depending upon any variable as K. And next one is the cost, that is the depreciation as well as the interest of the cost of your capital layout is proportional to the area of cross section, hence it is K1A. So K0 plus K1A is equal to C1. Again, K0 is another constant that is being considered. Obviously, C2 doesn't have any difference because the major part of the running cost is nothing but the losses that is being encountered. So C2 will be with K2, sorry, K2 divided by A. So now, as usual, in order to obtain the minimum or maximum condition, we have to differentiate a particular equation with the variable. So the total cost equation is C1 plus C2. Here now the C1 is equal to K0 plus K1A. Hence, K0 plus K1A plus C2 is K2A. Okay. So I'm just going to differentiate that by a variable, that is area of cross section, and again we'll just get the same as and equate it to 0. And so have K1 is equal to K2 divided by A as usual. So what is the statement for the modified Kelvin's law? It suggests that the most economical conductor size is that for which the annual cost of the energy loss is equal to the annual interest and depreciation for that part of the capital cost, which is proportional to the conductor size. So the graphical illustration of the modified Kelvin's law is shown as shown over here. C1, C2, and obviously the economical size of the conductor is the lowest point. Okay, so XY is going to tell about the annual minimum annual cost, and OX is going to tell about the area of the cross section. Where here we are just including the total annual cost by considering the supporting structure cost as well as the insulator cost. Thank you.